Welcome back everyone. In this lesson we are going to learn about a very popular method for finding out the solutions of simultaneous linear algebraic equations, which is known as LU decomposition. In the last lecture we have learned about matrix inversion and how that matrix inversion can help you to solve a system. So we have used the adjoint method to find out the inverse of a matrix, but that adjoint method is not efficient for computational applications or implementations. And we will see in this lesson that to inverse a matrix, LU decomposition is very much important and it's very efficient. And this LU decomposition method can also help you to find out the solutions of a simultaneous linear algebraic equations. So let's dive into the details of LU decomposition. We have already known about Gaussian elimination and Gauss-Jordan method, and we have also seen the naive approach and the complete Gaussian elimination. And in all of those methods, the first step was to eliminate the off-diagonal elements. In Gaussian elimination, we converted the original coefficient matrix into the upper triangular matrix, but in Gauss-Jordan method, we have converted our original coefficient matrix into an identical matrix. So, and in Gauss-Jordan method, all of the off-diagonal elements are zero or vanished. So that's the elimination step of Gaussian elimination or Gauss-Jordan methods, and you have to remember that this elimination step is very much time consuming because you have to do a lot of calculations. There are lots of additions, multiplications and subtractions and divisions in all of those steps, and that's very time consuming if you consider from the perspective of computational efficiency. And that's why LU decomposition technique was invented to circumvent that elimination step. So this LU decomposition method can be implemented easily, and it's very efficient for computational purposes to implement this elimination step. Also, another application of LU decomposition is that it can be easily implemented to find out the inverse of a matrix. Previously, we used the adjoint method to find out the matrix inversion in the last lesson, lesson 21. But in this lesson, we will see that LU decomposition is far more efficient than the adjoint method to find out the matrix inversion. So let's find out what's the algorithm of LU decomposition. Let's say we have a system of linear equations which are denoted something like this. A is the coefficient matrix, X is the vector of unknown variables, and B is the constant vector. So we have to find out the unknown variables X. Okay, so the purpose is to decompose the coefficient matrix into different matrix. So that's the main thing. We have to decompose the A matrix into two separate matrices. The first matrix is called the L matrix, which is an lower triangular matrix, and the next matrix, the second matrix, is the upper triangular matrix. Okay, so this L is the lower triangular matrix, and the other matrix, which is known as U matrix, is the upper triangular matrix. And if you multiply these two matrices, L times U, it's a matrix multiplication, then you will get the original A matrix. And that's why this is called an LU decomposition technique. L is for lower triangular matrix and U is for upper triangular matrix. Look at this, the lower triangular matrix is very specific. The diagonal elements are 1, and we have to find out these off diagonal lower elements. So that's the purpose of finding out the L matrix. And on the other hand, the U matrix is also very straightforward, and the lower elements below the original diagonal is 0, and we have only the upper triangular elements. So that's the upper triangular matrix. So we have to find out these terms, L21, L31, L32, and in the upper triangular matrix these terms, U terms. So that's the main purpose. We need to find out these two matrices, L times U, and later we will see that with these values, with these two separate matrices, we can easily find out the solutions of linear algebraic equations, or we can find out the matrix inversion. So this is the step 1. We need to decompose A into L and U. The next step is the substitution step. Look at this. L is the lower triangular matrix. Okay, so if you multiply L with an element matrix, and that is known as the D matrix, then we will get the B matrix. So this is the main formula, another formula that is used to find out the solutions. If we multiply the L matrix with another matrix, say D, and we will get the resultant as the B constant matrix. So from these formula we will get the D matrix, the D elements. So once we get the D elements, and we will use this formula, which is U times X minus D equal to 0. U is the upper triangular matrix, X is the original unknown vectors, and D is the matrix that we have determined from the previous formula. So from these formula we know the U matrix, we know the D matrix, only we have to calculate the X matrix. Okay, so this is a backward substitution method. In the last case where we used the L times D equal to B, that was a forward substitution method, but this one, in the step 3, this is a backward substitution method. So all of these steps are summarized in this figure. We have this original equation, system of equations, A times X equal to B. The first step is to decompose it into upper triangular matrix and the lower triangular matrix. Then from the lower triangular matrix we use this formula as a forward substitution method to find out the D matrix, and then using the D matrix and the upper triangular matrix we will get the X matrix or the unknown vector. So this last step is the backward substitution. So the first substitution was forward substitution and the last one is backward substitution. So these 3 steps constitute the LU decomposition algorithm. Now let's find out how we can implement this algorithm. First we need to find out the lower triangular matrix and the upper triangular matrix. So let's first find out the upper triangular matrix. If you remember from lesson 19 or lesson 20 where we used the Gaussian elimination methods, we first converted the original coefficient matrix into an upper triangular matrix. So that's the upper triangular matrix, that's the same upper triangular matrix that is used in LU decomposition. So in the first step, if we use Gaussian elimination step, that is the first step of Gaussian elimination approach, you will get the upper triangular matrix. So this is the same calculation, the procedure is exactly same that we used for Gaussian elimination to convert the original matrix, original coefficient matrix into the upper triangular matrix. So this step is already known to us. Also, if we look carefully in the whole process of Gaussian elimination, we will see that in the same process we can get the L matrix. So first of all, how we can get the L matrix? This is the coefficient matrix and we convert this matrix into an upper triangular matrix in the Gaussian elimination method. But in the same process we convert this original matrix into the upper triangular matrix, that means this one. Okay, but in the process if you remember, what were the multiplicative factors to convert these matrix into the upper triangular matrix? If you remember, to remove these 2 elements, the first 2 elements from the first columns, A21 and A31, we first multiply the first row with this value, A21 divided by A11. A11 is the pivot coefficient and the first equation was the pivot equation. So the first multiplicative factor for this location to remove these point below the original diagram, the primary diagonal, the multiplicative factor is A21 divided by A11. And similarly, to remove this term A31 from this matrix, the multiplicative term was A31 divided by A11. So these were the two multiplicative factors that were used to multiply the first equation and then subtract from the second and third equations. And finally, we can remove these two terms below the primary diagonal. And the final step, if you remember, we have to remove all the lower elements below the primary diagonal of the matrix, and we will see in the multiplicative factor for the last element in the second column, which is something like this, A32 prime divided by A22 prime. So these multiplicative factors are actually the elements of the lower triangular matrix. That means we can easily get the lower triangular matrix with these multiplicative factors, the F21 factor, F31 factor and F32 factor. So if we substitute these multiplicative factors into these matrix, we can easily get the lower triangular matrix. So you see, in the lower triangular matrix and the upper triangular matrix are generated in the same process, in the Gaussian elimination step that we had used previously. So this is not a separate algorithm or separate method, actually the same approach and the same procedure that we had followed in the previous few lessons for Gaussian elimination. So finally, it can be shown that the whole matrix, A matrix, can be easily reconstructed by multiplying the lower triangular matrix with the upper triangular matrix. So if we multiply these two matrices, we can easily get back the original coefficient matrix. So that was the LU decomposition part. So let's look at an example so that it becomes more clearer to you. So say, for example, we have this system of equation with three equations. There are three equations, and we need to find out the lower triangular matrix and the upper triangular matrix based on the Gaussian elimination method. So what we need to do, we construct the coefficient matrix from the coefficients of these equations, and that is this equation, this matrix, A matrix. This is the original coefficient matrix. And in the same process that we followed for Gaussian elimination to convert the coefficient matrix into the upper triangular matrix, we convert the matrix into this upper triangular matrix. So this is the same procedure that we followed for Gaussian elimination. So I am not showing the details calculation. Please do the calculation at home by your hand so that you can understand the procedure. So that's the upper triangular matrix. So in the same process, we can easily get the lower triangular matrix if we can remember the multiplicative factor at each step. For example, in the first step, the F21, this multiplicative factor would be 0.1 divided by 3. Similarly, F31 multiplicative factor would be 0.3 divided by 3. And for this one, the multiplicative factor would be after the first step. After we had eliminated these two terms, we can get this multiplicative factor from the modified matrix. So F21 is 0.1 divided by 3, as we already said. It is 0.003333. F31, this is the F31 multiplicative factor. And the element A32 prime was eliminated by using the factor this. So this multiplicative factor can be achieved after we had removed the first two columns from the original matrix. That means after we had removed the first elements from the second and third row, we can get the third multiplicative factor. So this is the third multiplicative factor, which is minus 0.027130. So all the multiplicative factors are at our hand, and we can easily substitute these values into the lower triangular matrix. In the F21, in this location we substitute the F21 multiplicative factor, and in this location we use the F31 multiplicative factor, and in this location is the F32. So this is the lower triangular matrix, and we had already got our upper triangular matrix. So this is the decomposition technique for LU decomposition. So if you multiply these two matrices, the lower triangular matrix and the upper triangular matrix, if you multiply these two matrices, we can easily get back our original A matrix, original coefficient matrix. So if you multiply these two matrices, you see we get this result. Okay, but there are some slight discrepancies. For example, the first element of the second row in the original matrix, it was 0.1, but in this case, whenever we multiply these two matrices, we get the value to be 0.0999. It's almost equal to 0.1, but not exactly equal to 0.1. Similarly, this last element, which is 9.99996, it should have been exactly equal to 10, but it's not. So what does this mean? Is our decomposition wrong? Is the decomposition method was not proper for this matrix? That's not the case, because whenever we calculated these values, for example 0.0333, we actually considered as finite significant digits. Similarly for this one, for these calculations, we actually considered the terms that were used in our calculator. We just truncated the higher terms, higher digits. So that's why we had these slight discrepancies, but that's not a big problem here. We had just shown that if we consider a higher number of significant digits, we can easily get back to the original matrix. So that was the part of the LU decomposition. Next, in the step 2, using the L matrix and the constant matrix, we can get our intermediate values, intermediate unknown values. These d1, d2, d3 are the intermediate values. Okay, once we get these intermediate values from this equation, we can use these values with the upper triangular matrix to find out our original solutions. So these are the intermediate solutions, these are not the final solutions. So our L matrix, the lower triangular matrix, looks like this, and this is the intermediate solutions, and this is the B constant vector. So if you multiply this matrix, if you multiply with matrix multiplication, you can easily form these three equations. Okay, these are the three equations from this matrix equation. So look at the first equation. In the first equation, we only have the d1 term. Okay, so d1 is directly notified here, which is d1 equal to 7.85. so once we determine the d1, we can easily substitute the value of d1 into the second equation, and then we can get the value of d2. And after that, we have determined the d1 value, and from the second equation we have determined the d2 value, and we substitute these two values into the third equation. And in the third equation, the only left unknown variable is the d3. So we can easily find out the value of d3. So look at this, the approach, it's a forward substitution method. We start with the first equation, then second equation, then third equation. So this is the forward substitution method. In the Gaussian elimination approach, if you remember, we used the backward substitution method. That means we started from the last equation, then we gradually substituted the values into the higher terms, into the higher equations. Okay, so from these three equations, we can easily get the values of d1, d2 and d3, which are shown in this slide. d1 equal to 7.85, then we must substitute this d1 into the second equation, then get the d2, then with the help of d1 and d2 we can get the d3. So this is the D matrix, our intermediate solution. This is not the final solution. With these matrix we can get the final solution with the help of upper triangular matrix. So in the last step we use this equation, if you remember from the algorithm, which is the upper triangular matrix multiplied by the original unknown vector matrix vector and equal to the D matrix, which is the intermediate solution. So if you remember, this is the upper triangular matrix, and we can easily form 3 equations from this system. Okay, now we have to do the backward substitution, because look at this system. In the last equation we can easily get the x3 term. That means once we get the x3 term, we can substitute the value in the second equation, from where we can easily get the value of x2. And then after that we can substitute the values of x2 and x3 into the first equation to find out the value of x1. So this is the backward substitution. We start from the last equation and gradually move to the upper equations, and that's why it is known as the backward substitution. So this step is very much similar to the Gaussian elimination method. So I am not showing the detailed calculation of this approach. Please do the calculation at home. This is a very straightforward calculation. So once you determine the values of x1 and x2, x3, those would look like something like this: 3 minus 2.5 and 7.00003. So this is our final solution. So in this way we can easily use the LU decomposition method to find out the solutions of a system of linear equations. So in this method, in this lesson, we have learned about the LU decomposition technique, and we have seen how the lower and the upper triangular matrix can be easily determined with the help of Gaussian elimination method, the basic Gaussian elimination method. So that's the main theme. That was the main theme of this lesson, and you see there is no new algorithm. Actually, we can easily go through the procedure of Gaussian elimination to find out the values of L matrix and U matrix, and after the decomposition we can use those two matrices to find out the solutions. So we have already seen this in our example. So please try out the MATLAB code in our LU decomposition segment. So I have attached the MATLAB course with this lesson. So please go through the details of the course. In the next lesson we will see that there are some other aspects of LU decomposition. So we will go into the details of those properties in the next lesson. So till then, thank you so much.